is still dry. All right, the paint is still dry on this tutorial. So I'm still going to be working on fixing bugs. So if you do grab it, make sure and pull periodically. So one of the things we talked about last time was that, and I think Uriel asked a question that triggered some of this, is that if we want to design a camera for a robot, maybe it makes sense to do more than just use a neural network that's trained on regular images. Maybe we should train on the images we capture with our camera. And that was a little bit more scope than we covered last time. But I dug in a bit more and put together a little tutorial on how you can do that using ISET and Matlab if you want, and you can start to play with that as a possibility. So you can design a camera, train it on images, and then see how it performs. And this is really, this tutorial is a framework that you can then use. So if you wanted to actually do a project with it, you'd obviously want to enhance it and modify it and mess with it. But if you just want to learn something, you can probably walk through it fairly successfully. So it's in the classroom folder in the Psych 221 repository. And basically, we talked last time about the Camera Designer app. It's one way you can design a camera. Brian and Joyce and I are talking about lots of other ways. But basically, you want to get started by having a set of optics, a sensor, and an image pipeline that you're familiar with, or sorry, that you've designed. And then what we do is we take a pre-trained network, and here we've used SqueezeNet. You could use ResNet 50. SqueezeNet's just a little faster and smaller to train. You don't have to download it separately. So it's a little quicker shortcut, but if you're really going to do a project, you could switch out and use ResNet 50 just as easily. So the idea of transfer learning, and I'm not going to try and read all this text, but if you go through it, all this stuff gets described in more detail, is that it's very expensive to train a full image recognition network. It's thousands of hours of machine time, typically done by big companies once in a while to win contests or ship product. But then somebody came up with the fabulous observation that most of the layers of a pre-trained network are just generally pretty smart about the world, no matter what world it is. So those are called the feature recognition layers. So at a low level, a feature recognition layer might recognize horizontal edges or diagonal edges. And at a higher level, a feature layer might start to recognize, well, even stop signs or faces or things that look like other things. And surprisingly, it turns out they're pretty robust and can be used for a lot of different things. So what we want to do is replace the final layers, which just take those features and learn how to classify the objects that are of interest to us. And then we can train, or it's called transfer learning, but we can train just those top layers much, much more quickly. So it might take 20 minutes or something to retrain a simple, well, not a simple network, but to retrain for a simple classification problem. A network that trained from scratch would take 10,000 images and a month. So what we're going to do here is we're going to load SqueezeNet. We'll replace the final layers. We'll train the network, and then we'll see how well we did. So the first step is to get some data. I've created a data set here that you can, I need to go to the live editor in this live script, and I can say run section. Basically, I took, I don't know, 500 or so of my mammal photographs that were randomly selected out of 4 species categories, leopard, lion, hyena, and cheetah. And they're not particularly good or bad. I literally had a randomizer pick them out. And I put them up in Canvas, and in theory, and it seems to work pretty well, we can actually pull right from there, and then it pulls it down and unzips it. But basically, anywhere you want to get a set of data, there's 4 other data sets there you can use. You can make your own. All you really need is a top-level folder, and then each class of images gets its own folder under that. And it can be anything in the world, dogs and cats, or you can use the web image browser we put up earlier to get them. And then you want to launch the Deep Network Designer, which is the tool that is in the Deep Network toolbox, or somewhere in Matlab you can get to under apps. If you have the deep learning toolbox installed, you might need to go to the apps tab and search for it and install it if it's not already there. And then we import our data. Oops. I'm actually doing this on another computer, and it doesn't, when I screen share, it always gets the stuff wrong, because my other computer has a better GPU for this. So we want to browse for our data. And I've got it in, oops, not data local. The default location. We tend to put everything we download during these sessions in local. So local comes kind of empty on the repositories, and it gets filled up with whatever stuff gets downloaded. Now we could import this data as is, but there's another step which is kind of optional, which is if we don't have a ton of data, one of the things computer scientists do is augment it by basically modifying the data in different ways to teach the network as if it had more original data. So in this case, we're going to randomly reflect them around the x-axis, not the y-axis, because animals don't look the same upside down. We can randomly rotate them. I'll use 90 degrees plus or minus here. That might be too extreme. And then we can rescale them. I'll say from 1 to 2. And so you can play with that, but that's just to pretend we have more data than we do without having to start over with it. The other thing that's very important is we need to separate some of our data into what's called a validation set. So basically this is like the closed book test at the end of the course, is we're going to train on, in this case, 70% of our data. And then periodically, every few iterations, we're going to check and see how we do on the other 30% of the data. Now those numbers 70 and 30 are kind of arbitrary, but now we can import the data. And Matlab will give us, well, it's not showing a pretty picture at the top. For some reason over the remote connection, it doesn't want, normally it would show us a table of the amount of data in each class, and these would have, oh, it's just being a little piggy. I think the remote sharing may not be its friend. Here we go. So we'll see how many things we have in each class. We get some random examples that we can play with. So now that we have that, we want to go through and look at our SqueezeNet. So we go to the Designer tab, and we can use Control and then the mouse wheel to zoom in. And what we need to do is replace just the classification, well, just the last two of the last layers. This last convolutional layer needs to be fixed because it's hard-coded to output 1,000 entries, because that's how many are in the ImageNet data set on which it was trained. So what we want to do is pull over a convolutional 2D network. Now, I don't know why. For some reason, the network designer doesn't let us just change the parameters on the existing ones. That must be because of the way it's a pre-trained network. But we basically just replace it with ours. And then we set the properties. The filter size of the old one was 1.1. I'm not going to talk about why or whatever. But now we need 4 filters for our 4 mammal classes. So whatever number of data classes you have is the one you're going to want to use there. And we do the same. We just replace the classification layer because, again, it's hard-coded to 1,000 for some reason, whereas if we just add one from the palette, it's smart enough to realize it should be automatic, and it doesn't have any setting at all. So now what we've done is we've created a network that, oh, I forgot something important. We want to make sure that our network trains the 2 layers the convolution layer we just added, and not all the other layers. So we're going to do a little trick, and the way this trick works is different in TensorFlow, it's different in Mathematica, but this is how they do it in Matlab Deep Learning Toolbox. We increase the learning rates, and this is all documented in the tutorial, so you don't have to be taking notes on it, on our layer. And then when we go to training, which we're going to do next, we're going to set the training options so that the training rate for the network is very low. I think I did this right. Where's my, oh, initial learning rate. We're going to add 2 zeros to it. And so that's going to mean that most of the layers, we don't waste time trying to retrain. This thing has 68 layers, so it's not going to get trained by us easily. I'm going to say we want to validate every 10 iterations. We'll just run like, we could be able to run 10 epochs. An epoch is each pass through your entire data set, and the batch size is how many images it processes before it updates the weights. And you can read all about those. I'm not going to try and teach you a whole AI course in one tutorial. We close. And then in theory, we can train the network. It's giving me these error messages, but they're from something. Let's see if this works. Yeah, Matlab is pretty good. It does stuff like data normalization. A lot of the stuff you learn about in the first 4 weeks of your average AI class, the good frameworks actually do for you. So it's good to learn how to do all this stuff like data normalization and dropout layers and everything. But a lot of that gets regularization. A lot of that has been made much, much easier with these modern frameworks. So it's starting training. Iteration 1 out of 100, you can see basically we're going to run, we told it, I guess, 10 epochs on the number of data, the amount of data we have. So it's going to run through all of it. So as far as the tutorial, the next piece we'll get to, and I'll actually walk through part of that while this is running. I think I can at least talk about it. So that's going to give us a baseline. That's going to say, okay, if we just take the raw images, how well did we do? So the next thing we're going to want to do, we've done all this, we did this, we did this, we did this, we did this. So you can see it's all documented in there. We just did this, and this is what the output's going to look like if we're lucky. Then what we want to do is train your camera design. And basically there's a lot of kind of gory code in here that you really don't need any of if you know how to use ISET and just design the elements you need, which are the optics, the sensor, and the image processor. So all this is trying to do is get you one of those somehow. And once you have one, what you get to do is down here, this code runs exp classify, the classifier we learned about last time, except we've told it not to actually do any classification. The classifier key is blank. What we've told it to do instead is just generate the simulated images through our camera. And it's going to put them in this our IP data subfolder, which is this by default in this case. And then what we want to do is basically we just are going to load that folder into our same network and retrain it and see how well it does. And so we can train different cameras, and you can have as many of these you want as long as you put them in different folders. And you can train different cameras and see how they perform, how the network performs when trained on a monochrome sensor, or which I was trying to do before the class. I didn't get it done in time to show you that, or a big sensor, a little sensor, fixed focal length lens, or whatever. And here we go. So our training session finished. It took, what does it say? Oh, it took 2 minutes on my 1080. If I run it on this machine that has an AMD GPU, it doesn't train on AMD, so it takes 10 times longer. And you can see we got to a training accuracy of over 80%, but our validation accuracy really topped out at about 70. And that's one reason we do validation, is because eventually the network starts cheating. And if you have too little data and too big a network, it starts memorizing the answer. And I talk about that in the last part of the tutorial. So we test on our design, which I just described. You can save any or all of this. I talk about that in here because you might want to save your updated network. You might want to save your training results, save your camera design. And then this appendix talks about overtraining, where I ran one of these for a very long time. And you can see the validation just floors out as the network gets all the way to almost 100% accuracy, but the validation peaked here. So typically, if you do this for real, what you want to do is checkpoint your network's progress every once in a while. I haven't seen how to do that in Matlab yet. I need to look that up. And stop when you get the highest validation result, not the highest training result. But you can also kind of do that manually by figuring out how much to train before you stop. So that was a super huge, super quick run through. And I should have stopped a few times and asked for questions, but we didn't have a lot of time. So I'll ask for questions now.